Next bit, dynamic equilibrium. So you know the definition of dynamic equilibrium is basically referring to a reversible reaction. So it's a reversible reaction. And then we know it's to do with two conditions. Okay, there are two particular conditions where the rates of the forward and backward reactions are equal. The rates of forward and backward reactions are equal, but that is just the first half of the story. Also, this is the very important one, the concentrations of the reactants and products are not changing. They are not necessarily equal, but what is important is they are not changing. It is the rate that are equal, but the concentrations are not necessarily equal, but they become constant, meaning to say they don't change anymore. Alright? So constant does not mean equal, constant means not changing. You increase pressure, but you keep temperature constant. Alright? You want to talk about the composition, because sometimes they can ask you position. So here composition refers to yield, not position. Okay, but they are of course related. Alright, so this is the idea of using something called Le Chatelier principle. He's a French guy. You might not know his name, which doesn't matter, because whatever he said is just a principle. You will have used it in your explanation throughout your O-level anyway, without even knowing the guy's name, yeah? So what does he say? He said that when you have a system in dynamic equilibrium, if you change something in the system, if you change something into the equilibrium will try to oppose that change. It tries to counteract. It tries to go against the change. It tries to go opposite to the change. So I've given you a few definitions there, alright? So when you don't change temperature, we are not concerned about enthalpy change. We are looking at the number of moles of gases. Okay? They don't show the number in front. That means it's 1, 1, and 1. Okay? I'm going to explain first because it's easier to explain first than predict. So I calculate and then I state. There are 1 mole of gas. Gas is very important because the gas exerts pressure. So you got to specify the gas on the left side of the equation. But 2 moles, again, of gases. Gases are very important on the right side of the balance equation. So what does it mean? Increasing pressure. So gases exert pressure, you see. Gas exert pressure. When you have more molecules of gases, they will exert more pressure. Pressure is force over area. So the gaseous particles are pushing more and more onto the walls of the container, the contender. Okay, that's why they exert more and more pressure. So what is going to happen is increasing pressure will make the system, or you can say the equilibrium, shift to the side with, when you increase pressure, the system wants to decrease pressure. So there's 1 molecule of gas, 2 molecules of gas. So the system wants to decrease pressure, it will shift to the side with lesser gaseous molecules, would mean lesser pressure. So that's what the equilibrium will do to oppose the change. So it will shift to the side with lesser gaseous molecule. Therefore, it will shift to the left. It will favor backward reaction. When you favor backward reaction, what happened to the composition of the equilibrium mixture? The thing is, they talk about the mixture, they do not talk about this, they do not talk about this, they do not talk about this, they talk about the mixture. So you need to be careful there. Because my prediction was it will favor to the left, it will favor backward reaction. So in terms of the composition of the equilibrium mixture, in terms of composition, amount of PCl5 would increase, But you must also talk about the other composition in the mixture, because they did not specify any, right? PCO3 and Cl2 will decrease. Decrease in what? Decrease in the amount. Because you shift the equilibrium to the left, so you will get lesser of this to increase in the amount of this. Alright? Now, you increase the temperature, but you don't change pressure. When you don't change pressure, we are no longer looking at these things which involve working out the number of moles on the left and on the right. Okay, we need to look at enthalpy change. Do we know anything about enthalpy change? Oh, okay, I see. So they are not asking you to predict now. They actually give it to you. When you increase temperature, the equilibrium move to the right. Why is that? Alright, well, let me think about it. Let me walk you through it. When temperature increase, equilibrium shift to the right. Alright, so you need to work out, is the going from left to right, is the forward reaction, does it absorb heat or does it release heat? If it absorb heat, it's endothermic in the forward direction. If it release heat, then it is exothermic in the forward direction. When you increase temperature, your system wants to do the opposite. Your system wants to decrease temperature, right? So when temperature increase, your equilibrium wants to decrease temperature by shifting to the right. So that means you must have absorbed heat on going from left to right. That's why you like to absorb this heat. Only then you can reduce the temperature. That means the forward reaction must be endothermic. Alright, so suggest why the forward reaction is endothermic. I mean, that's how you would start off in explaining this kind of equilibrium prediction, if they actually give you the enthalpy change, right? But here they don't give you, so they just want you to come up with the idea on the enthalpy change. Let me walk you through it. If the forward reaction is endothermic, when you increase temperature, the forward reaction will absorb more heat energy to try and reduce the temperature. So in absorbing more heat, it will favor forward reaction, and therefore it will shift the equilibrium to the right. Therefore, it will shift the equilibrium position to the right. Next bit is about rate. Rate of reaction has got nothing. It has got zero thing to do with enthalpy change or whatever. Rate has got everything to do with collision theory. And we are talking specifically about temperature. So there are two things you need to think about. Alright? Temperature is a measure of kinetic energy, which is half mv squared. That is your relative velocity of your particles, your reacting particles. Yeah. So as temperature increase, reacting particles will move faster. So when they move faster, they will collide more frequently. So you increase the frequency of collision. That is why rate will increase. However, also the proportion, not only you increase the collision frequency, but the proportion of molecules or reacting particles, the reacting proportion of reacting particles with enough energy, meaning to say your energy is greater than or equal to the EA. Alright, sorry, so I should be there, with enough energy which is greater than or equal to the activation energy of the reaction, will increase as well. Okay, therefore you get more effective collision, or you will call this successful collisions, meaning to say the collisions that will lead to reaction. Okay, that's why the rate of reaction increase. Right, this last line is just to complete a sentence, really, the whole idea, really. But there are two completely different ideas. One is collision frequency. One is to do with the proportion of effective collision. That's to do with, do you have enough energy to overcome the activation energy? Yeah. Okay, so that's why the rate is important there. State and explain in terms of particles what happened to the rate of forward reaction. So they want you to state, they want you to explain, they want you to talk about rate, they want you to talk about the particle theory as well. So we know that temperature is a measure of kinetic energy of the particle. So as temperature increases, particles gain more kinetic energy. So when kinetic energy is to do with movement, right? So they move more rapidly. Rapidly. Okay. And in a way, they will collide more often as well. Therefore, collide more frequently. But what is more important, however, is to do with energy distribution. So when you change temperature, you really change the energy distribution such that there are more particles, or there are greater proportion of particles with higher energy that is greater than or equal to the activation energy. So you need minimum activation energy to kickstart a reaction. So when you increase temperature, you have more particles that have higher energy, and there are greater proportion of those particles with higher energy greater than or equal to EA. Therefore, you also get more effective collision, or what you would call successful collisions in all level. And as a result of that, your rate of reaction will increase, meaning to say they get faster. The rate increases, the reaction gets faster. Okay? So now they're asking on the position of equilibrium as you increase the temperature. So this is to do with Lee-Chatelier principle. You might not have heard this particular phrase before, but you will know how to apply it subconscious. I mean, like your school teacher might have covered it without necessarily stating the term or the phrase itself. So basically, we are talking about position equilibrium now. So we need to consider what is the enthalpy change of the forward reaction. The forward reaction here is exothermic. You see, they actually told you. Sorry, that goes further down. Since the forward reaction is exothermic, what does exothermic mean then? It means that it releases heat energy to the surrounding, yeah? Okay. So as you increase temperature, that means what will the system try to do? The system, which is the equilibrium, will try to oppose that change, you see? Will try to decrease the temperature, because that is your change. Your system, which is in equilibrium, will try to decrease that temperature. How would it do that? The forward reaction releases heat, right? So I want to decrease temperature by releasing less heat. So the equilibrium will release heat, but I can try and decrease the temperature to oppose this change by releasing less heat. And if I release less heat, therefore equilibrium position will shift to the left, because my forward reaction releases heat. If I release less heat, I will favor less of the forward reaction. I will favor the backward reaction. My position therefore will shift to the left. I have stated what happened to the position. I have explained why that is. Okay, and therefore that's how you get the full mark, by talking about Lee-Chatelier principle without just stating the principle itself, but actually explaining it. Okay. Next bit, they want you to state, explain in terms of particle, rate. So they increase the concentration of ethanoic acid. So we are talking about effect of concentration on the rate. Ethanoic acid is a reactant. Okay, reactants will need to collide with reactants to form product. When you increase the concentration of reactant, okay, as the concentration of CH3CO2H increases, what's going to happen is we are not going to talk about Lee-Chatelier principle, because we are talking about rate. We are not talking about equilibrium position or equilibrium yield. We are talking about rate. Therefore, I'm going to use kinetic particle theory. Sorry, not kinetic particle theory. What am I talking about? Collision theory. So this is to do with rate of reaction. Yeah, okay. So you have more CH3CO2H molecules per unit volume. What is the unit of concentration? Unit of concentration is mole per dm cube. If your concentration increase, it means there is more mole per dm cube. If there's more mole per dm cube, there are more molecules per unit volume. Okay, and because of that, therefore, you can get more CH3CO2H molecules collide with each other. So you get collision frequency. Collision frequency will increase, and therefore, so we are not. How do I say this? They collide more frequently. Therefore, your rate of forward reaction will increase or become faster. Now, this is the part where they ask you position of the equilibrium. The water form is removed. State and explain. Okay, so I would rather explain first because it's a lot easier to figure out the thought process. It really doesn't matter if you explain first and state later because it's still part of the whole answer. When they look at it, it's still going to be there. Okay, so what's going to happen then? This is an equilibrium. So it's governed by Le Chatelier principle. I'm not sure if you heard of it or if your school teacher will mention it because I'm not sure if it is specified in the O-level syllabus. But if you have covered equilibrium, there's almost no way you wouldn't have used Le Chatelier principle. Whether you explicitly state Le Chatelier principle or not, there's another thing. This is a product. If you remove the product, what is this equilibrium going to do? If you remove this product, the concentration of water will go down. This equilibrium will try to overcome the change, which is a decrease in the concentration. It will try to increase the concentration of water. Because you have decreased the concentration of water by removing it, equilibrium will try to produce more water to increase the concentration of water. And how does it do that? It will shift to the right hand side to produce more water. When you shift to the right hand side, it will favor forward reaction. When you favor forward reaction, it will give you more ester in the meantime as well. But the question is not asking you on the yield, it's asking you on the position. So be very careful on it, yeah? As the water is removed, then the concentration of water will decrease. So what would your equilibrium do? The equilibrium will try to increase because Le Chatelier principle says the equilibrium, which is the system, it will try to do the opposite to oppose the change. So it will try to increase the concentration of water, that is to favor forward reaction, or we can say to shift the equilibrium to the right. And guess what? That is the position of the equilibrium. Done. And I've also explained it as well. So the thing there is, it is called Le Chatelier principle. I mean, just knowing what the principle is called does not help you to explain it at all. But unless you know how it's being used, then it's going to be useless to know the name itself.